Okay, let's dive right into this. Welcome to our explainer on data averages and the, believe it or not, drama of variance. You know, we hear the word average thrown around constantly, right? But there is actually this whole hidden world of mathematical beauty and, frankly, tension hiding just beneath the surface of those everyday numbers. So think about this. If you have 1,000 test scores, how do you actually find the truth hiding inside them? That's the ultimate problem we're tackling today. We are constantly bombarded with massive amounts of messy, real-world data. And if we just stare at a raw list of 1,000 numbers, well, we'd get completely overwhelmed. We desperately need a reliable way to summarize that reality, to find the actual truth hiding inside. Which brings us to Section 1, the 3 statistical averages. To make sense of all this chaotic data, we rely on what I kind of like to call our cast of characters. These are the 3 fundamental tools we use to organize datasets before we get to the real star of the show. First step in our cast is the median. Now, the median is simply the middle score in a group of scores that have been ranked in order of magnitude. Imagine literally lining up all your data points from smallest to largest. The median just walks right up and cuts that line of ranked scores straight down the middle into 2 perfectly equal halves. Next, we've got the mode. This is the most frequent value in a range of scores. I actually like to think of the mode as the absolute most fashionable number in your dataset. It's just the specific number that pops up the most often in your sample. Super simple, very straightforward. But then we arrive at the mean. By definition, this is the arithmetic average of a series of numbers. Now, unlike the median in the mode, the mean is the undisputed heavyweight champion of averages. It actually involves significant calculation, and as we're going to see, it's deeply embedded in the absolute most powerful statistics out there. Moving to Section 2, mastering the mean formula. We aren't just going to take the word average at face value. We're going to look under the hood. Now, what's really interesting about this slide is we get to see the actual mathematical mechanics of how the mean is built from the ground up. Now, I know. This might look like Greek to you, literally, but let's read the mean formula together. On the left side, we have an x with a line over it. We read that as x bar, and it simply stands for the mean. That equals the capital Greek letter sigma, which is just a fancy way of saying the sum of, followed by x, which stands for our individual scores, and finally, we divide all of that by n, which is just the total number of scores in our sample. See? Painless? You've literally just learned the foundational language of statistical formulas. On to Section 3, the crucial first step. So you might be wondering, why are we spending so much time specifically on the mean compared to the median or the mode? Why did we actually need to learn its exact formula? Well, let me tell you, its importance really cannot be overstated. Calculating the mean is the crucial first step for all parametric statistical tests. I absolutely cannot emphasize this enough. If you want to perform powerful parametric tests of significance, things like the t-test to compare 2 groups or an ANOVA to compare multiple groups, you absolutely must calculate the mean first. There is literally no way around it. You simply cannot do these tests without it. It is the absolute bedrock of inferential statistics. But that brings us to a rather massive question. What does the mean actually hide? Think about it for a second. If I tell you the average test score for a class is 60, okay, that centers us, but it tells us absolutely nothing about the individual students, right? Did everyone in the room score exactly 60? Or did half the class score 59 and the other half a 61? Or even more dramatically, did half the class completely bomb with a 0 and the other half get a perfect 100? The mean alone is totally blind to that reality. Enter Section 4, drama, mathematical sweat. To physicalize this concept of data spread, to really feel what the mean is hiding, let's look at this incredibly theatrical story about a new psychology professor named Susan Bowles and her, let's just say, very demanding chairperson, Dr. Terevsky, at Goat's Head College. So after a midterm exam where the average score was exactly 60, Dr. Terevsky demands to know how spread out the scores actually are. She's incredibly frustrated by Susan just reading off a boring list of numbers. So she commands, take this pile out to the stadium, read the score, and walk to the point it corresponds to. Just imagine the sheer theatricality of this. She literally forces Susan to place a physical mark on the field representing the mean of 60, and then physically walk the exact distance of each individual student's exam score away from that center point. Let's move to and see how this builds. Susan's exhausting process breaks down into 3 steps. 1. Mark the mean right in the center of the stadium. 2. Physically walk the distance of each individual score away from that mean. And 3, add up all those total distances. I want you to picture Susan out there on the field, absolutely drenched in sweat, trudging back and forth, over and over. What she's doing is perfectly illustrating that statistical deviation is literally the physical distance from the average. And the result of all that walking? Well, a large total distance from the mean means the scores are highly varied and really spread out. By the end of her absolute marathon, Susan's sheer physical exhaustion directly, mathematically translates to a large dispersion of students' scores. It's brilliant. Which leads us to Section 5, from sweat to variance. Now let's step off the stadium grass and transition back into the formal mathematics. Because exactly what Susan was doing out there with her physical sweat is precisely what statisticians do with numbers to formalize the official concept of variance. So, here is the formula for variance. Now, I know it looks a little complicated at first glance, but just remember Susan out there in the stadium. The top part of the fraction, the numerator, literally represents the total physical distance Susan walked from the mean. And then we simply divide by n to find the average of all those physical distances. That's it. Variance is essentially just the average of the squared deviations from the mean. Now, you might be wondering, wait, why do we square the deviations? So the crucial point is that raw deviations from the mean always, and I mean in absolutely all cases, add up to exactly 0. It's mathematically guaranteed. The positive distances on one side of the mean totally cancel out the negative distances on the other side. So by squaring them, we magically turn all those distances positive. This brilliantly preserves the true scale of the spread without actually changing the fundamental mathematical relationship of the scores. It's kind of a genius workaround. In statistical jargon, this top part of the variance formula, the sum of those squared differences we just talked about, is officially known as the sum of squares, or simply SS. And trust me, as you continue your statistical journey into more advanced tests like ANOVA, the sum of squares is going to become one of your absolute most vital tools. It is everywhere. All of this leaves us with one final, totally vital question. What is the true shape of your data's story once you step away from the center? Yes, the mean anchors us. It gives us a really solid starting point. But it's the variance, that literal mathematical sweat we just explored, that truly reveals the messy, spread out, fascinating reality of the real world hiding inside your numbers. Keep looking beyond the average and keep exploring.